the experiment conducted to study the photoelectric effect led us to conclude that radiation behaves as if it were a bunch of particles, while experiments conducted to study the phenomena of interference showed the wave nature of radiation. This particle wave nature of radiation was extended to matter by Louis Victor de Broglie. De Broglie hypothesized that moving particles of matter display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. Hence, if radiation showed particle nature, so should matter. De Broglie proposed that wavelength lambda associated with the particle is equal to h divided by p, where h is the Planck's constant and p is the momentum of the particle. But p is equal to m multiplied by v, where m is the mass of the particle and v is the velocity of the particle. This equation is called the de Broglie equation, and lambda is called the de Broglie wavelength. The dual nature of matter is evident in the de Broglie equation. The left-hand side of the equation has the attributes of a waveform, while on the right-hand side are the typical attributes of a particle. Let us calculate the de Broglie wavelength of a cricket ball of mass 0.14 kg moving with the velocity of 40 meters per second, and an electron of mass m and charge E accelerated through a potential V, and compare the impact of de Broglie wavelength on matter. The momentum of the ball P is equal to 0.14 kg multiplied by 40 meters per second. That is equal to 5.6 kg meter per second. The de Broglie wavelength is calculated by dividing the Planck's constant with the momentum of the ball. That is 6.634 into 10 to the power of minus 34 divided by 5.6 kg meter per second. The ratio equals to 1.18 into 10 to the power of minus 34 meter. The kinetic energy of an electron is equal to the work done on it by the electric field K is equal to EV. Let this be equation 1. The kinetic energy of the electron is also equal to P squared divided by 2m, where P is its momentum and m is its mass. This equation can be rewritten as P equals to square root of 2mk. Substituting the value of k from equation 1, we get P is equal to square root of 2mev. The de Broglie wavelength is now calculated by substituting the value of h and p, that is, h divided by square root of 2mev. Substituting the numerical values of Planck's constant h, which is 6.634 into 10 power minus 34 joule second, mass of the electron m, which is 9.1 into 10 power minus 31 kilogram, and charge on an electron E, which is 1.602 into 10 power minus 19. And simplifying, we arrive at the equation lambda equals to 1.227 divided by square root of V nanometers. At a potential difference of 120 volt, lambda is equal to 0.112 nanometer. For the ball, the de Broglie wavelength is beyond any measurement possible and hence can be considered as negligible. Whereas the de Broglie wavelength for the electron is of the order of the spacing between the atomic planes in crystals. This is the reason why macroscopic objects in our daily life do not show wave-like properties, whereas the de Broglie wavelength is significant and measurable in the subatomic domain.